So let's talk about another way that sound can interfere. So when we were talking in the last chapter, I mentioned the possibility of two speakers and they make sound and the sound waves can interfere. But in that case, I was making an assumption that both of these were the same frequency. So what would happen if you had two sources and you were adding two waves and they were different frequencies? Then what would happen is sometimes you get constructive interference and sometimes destructive interference. And so that would make this a more complicated sort of thing because you would end up with not all constructive or all destructive. So let's consider we got a wave here, and let's imagine a sound wave. And so that means that as you're standing here listening to the sound, then the sound comes in, and so the pressure changes P naught cosine omega t. Okay. And so this is going to be so we can talk about the sound waves, and it could be Y or P or whatever, it doesn't really matter. So the pressure is P naught cosine omega 1t, and then you have another sound coming in here, and that's going to be P naught cosine omega 2t. Okay. And so the total pressure is going to be P1 plus P2. So that's going to be P naught cosine omega 1t plus P naught cosine omega 2t. So in other words, P naught times cosine omega 1t plus cosine omega 2t. Now, in trig, you learned a trig identity, cosine A plus cosine B. Okay. And you might not remember it off the top of your head, but you do remember trig identities, and your trig teacher was saying, hey, you ought to learn trig identities because one of these days you're going to need to know them. Aha, the day is here. Okay, so cosine A plus cosine B is equal to 2 times cosine A plus B over 2 times the cosine of A minus B over 2. All right. So if I apply that to the problem that we have right up here, then what we've got is that P is going to be equal to 2 times P naught times cosine omega 1 plus plus omega 2 over 2 times cosine omega 1 minus omega 2 over 2. Okay. Now, what does that mean? Well, if you have two frequencies that are pretty close to each other, and then what's going to happen is that omega 1 plus omega 2 over 2, that means it's going to be oscillating like the average of the two. And then we have omega 1 minus omega 2 over here. That's the difference in the two. So if omega 1 and omega 2 are close to each other, sorry, there should be T's in here. Okay, if omega 1 and omega 2 are close to each other, then what we've got is the omega 1 plus omega 2 over 2 times T. Okay, and so you get the average, and then omega 1 minus omega 2 over 2 times T, and that's going to be close to 0. And then as T gets bigger, it gradually starts to do something. What will happen is you'll have something that'll be oscillating, and then it'll be gradually getting smaller, and then bigger, and then smaller, and then bigger. Okay. So that's the frequency right there, which is the difference between the two. But you're going to hear this peak and that peak. So instead of hearing omega minus 1, omega 2, the difference times T, you're going to hear double that. So in other words, you're going to hear a tone right here that this is going to sound like a tone right there. So you'll hear the average tone, and then you'll hear also that tone. Okay, so you're going to hear two different tones. They're not necessarily going to be the original tones. And so this is called beats. Now, if that, if you get they're very close together, these beats are going to be only a few hertz. Few hertz is actually subsonic. So what will happen is you will hear this gradually get louder and softer and louder and softer. So in other words, if you had two tones here, 212 hertz, and then you mix that with 214 hertz, then what you're going to hear is you're going to have to hear the 211 hertz, but you're also going to hear a 2 hertz beat. In other words, this tone will get louder and softer twice a second. Okay, now this is one of these interesting things that happens, and that is that you have, for example, musicians, and they they get together to play, and before they start playing and making pretty music, they're honking and squawking and hooting and making all kind of like horrendous sounds. What's happening is that adjacent musicians are trying to play the same note. Okay, now if it's exactly the same note, then you should get constructive interference and just get a big tone right there. But if the two notes are slightly off, what you'll get is this beat, and when they play the same note together, they'll be able to hear it getting louder and softer. And so they adjust until it's all steady. Okay, now what's happening here is that even though the musical instruments are supposed to be the same note, remember, if they're set up the exact same way, for example, a wind instrument or of any sort, brass or woodwind or something, remember that the speed of sound changes with temperature. So technically also changes with humidity. So if they had practiced before separately on different days with different temperatures and humidities, then even if they were playing the same note at that time, it's not going to be the same note right now unless they readjust. Likewise, string instruments. If the tension changes a little bit, it'll be off a little bit. And so it might not be enough off that the human ear can necessarily notice that the tone is off by half a hertz or something, so it sounds right to you. But when they play together, it's not going to sound right. And so that's kind of what's happening when they do that. Now, normally in class, what I do is I actually have a demo where I set up two speakers and I put slightly different tones in them, and you can hear the beat frequency. Can't do that here, but I'm going to link to a YouTube video here that does that. So the next lecture will do that. And then what I'll do after that is I will do an example problem here with beats.